Okay, let's jump straight into it. We're looking at a paper today that really tries to crack one of the biggest bottlenecks in 3D vision. For anyone who just wants a quick summary, the paper is E-RASER, Self-supervised 3D Reconstruction as Spatial Visual Pre-training.
And the bottom line is this. E-RASER is all about moving 3D vision into the world of scalable self-supervision. It's a way to learn from raw images without needing that slow, often clunky pseudo-labeled data from systems like ColMap.
Right, and the way it does that is the big trick here. It shifts from what its predecessor RASER did, this kind of implicit 3D modeling, to something much more concrete. It uses explicit geometry with 3D Gaussians. That's key because it stops the model from, finding shortcuts.
Exactly. That geometric grounding is so powerful that E-RASER just blows the old implicit approach out of the water on tasks like pose estimation. And what's really wild is that this self-supervised model is competitive with, and sometimes even better than, fully supervised models like VGGT. It's a fundamental shift.
So we've seen these massive foundation models completely change language and 2D vision. They just consume huge amounts of data and learn these incredible representations. But 3D has always felt like this missing piece of the puzzle. Why has it been so far behind?
That's a great question, and it gets to the heart of the problem. Why are our best 3D vision models still so dependent on fully supervised methods? And not just supervised, but often supervised with these imperfect pseudo-labels that come out of old-school structure for motion or SFM systems, things like ColMap.
And the big issue with ColMap, as anyone who's used it knows, is it just doesn't scale.
Precisely. It's inefficient. It can be brittle, especially in tricky scenes. And at the end of the day, it's just not a scalable solution if your goal is to train on, internet-scale raw video. To really get 3D vision to that next level, you need a self-supervised method that learns real 3D-aware features directly from pixels. No external geometry needed.
Before E-RASER, there was an attempt at this called RASER. It used this idea of latent-space view synthesis. But the new paper is pretty harsh on it. They call it superficial 3D awareness. What was the shortcut that RASER was taking? What made it so geometrically weak?
It's a fascinating problem. RASER was learning everything. The camera poses, the scene, the rendering, all inside this very flexible, latent transformer space. Because it wasn't constrained by the rules of physics or geometry, it found easier ways to solve the task.
So it was cheating, basically.
In a way, yeah. Instead of figuring out the true 3D structure of a scene, it relied on simple proxy tasks. A big one was just frame interpolation. It would use things like image index embeddings to figure out, oh, this is frame 5, that's frame 6, so the view should be just a little different.
Yeah.
It wasn't learning geometry, which makes it pretty useless as a general pre-training framework.
Okay, so E-RASER's mission is to inject this really strong, non-negotiable 3D inductive bias. How does the architecture actually change to make that happen?
The biggest change is they completely get the scene representation. They throw out the whole implicit architecture, the latent scene representation, the latent rendering decoder, all of it, and they replace it with explicit 3D Gaussians.
For our listeners who maybe aren't deep in NeurFs or 3D GS every day, let's just quickly break that down. You can think of 3D Gaussians as like millions of tiny, colored, semi-transparent clouds in space. Each one has a position, a size, an opacity, a color. And if you just project all of those onto a 2D plane from a certain camera angle, you get an image of the scene.
That's a perfect analogy. And the crucial advantage of 3D Gaussians and why they use them here is that the rendering process, that projection, is really fast. And most importantly, it's closed-form differentiable. That closed form is what provides the strict geometric regularization that keeps the whole system honest.
Okay, so let's walk through the data flow. How does it all work with this new grounded mechanism?
So it takes in a set of sparse view images and splits them into a reference set and a target set. First, a multi-view transformer predicts all the camera parameters, poses, and intrinsics. Then the reference images get encoded by another transformer, the scene encoder, which turns them into image tokens. And then a pretty lightweight decoder takes those tokens and directly outputs the per-pixel 3D Gaussian parameters.
So it's not learning some abstract latent code anymore. It's being forced to predict the actual physical properties of the scene, like distance, orientation, color, scale, opacity, all the stuff that defines real geometry.
Precisely. And the self-supervision loop is simple. You do the 3D Gaussians you just created, you use the camera poses you predicted for the target views, and you render what those views should look like using that differentiable renderer. Then you just compare your render to the real target image using a loss mix of mean squared error and a perceptual loss.
And this is where it gets really elegant. By getting rid of that complex latent renderer that RASER used, you're not just making the model simpler and faster, you're also forcing it to obey the laws of physics. It can't cheat anymore.
That's the beauty of it. The explicit geometry makes the whole pipeline interpretable and physically meaningful. It's exactly what was missing before.
But they also had to plug the other hole, right? The shortcut in the camera pose estimation. How did they stop it from just interpolating between frames?
You remove the main culprit, which was the image index embeddings. RASER used these, and it basically gave the model the answers. It was a huge temporal queue. E-RASER gets rid of them entirely. Instead, it uses a transformer structure, similar to the VGGT architecture, with this alternating local global attention to predict pairwise poses. This forces the network to actually look at the visual content to figure out the geometric relationship, not just the sequence order.
That makes perfect sense. You're forcing it to solve the geometry problem, not just a simple ordering problem. Like, what's the perspective shift here instead of what number comes after 5?
Exactly.
Okay, so explicit 3D modeling is clearly better from a geometric standpoint, but it has a really bad reputation for being unstable. It often just fails to converge if you train it from scratch, especially with wide baseline views. That's a massive practical problem.
Yeah.
How did they solve that with this fine-grained learning curriculum?
The curriculum is really the secret sauce that makes it all work. It's a stabilization mechanism. It carefully manages how difficult the training samples are by controlling the visual overlap between the input views. You start with the easy stuff and you gradually move to the harder stuff.
Like learning to walk before you run.
Right. You start with high visual overlap, so very small camera movements, almost identical poses. This lets the whole system initialize in a stable way.
And why is measuring this visual overlap so much better than what RASER did, which was just using fixed frame intervals?
Because frame intervals are a terrible proxy for difficulty. I mean, think about it. A 1-second gap in a video where the camera's just slowly panning is an easy problem. But 1-second gap in a high-speed drone video, that's an incredibly hard, wide baseline problem. A fixed interval is meaningless when you have diverse data. E-RASER needed a universal metric for difficulty that works no matter where the video came from.
And they came up with a way to calculate this overlap that's completely unsupervised, which is obviously critical.
Yep. They use 2 main methods. One is a geometric overlap, which is adapted from a covisibility metric. But the more interesting one, I think, is the semantic overlap, which is based on Dino v2 cosine similarity. Dino v2 is already a fantastic self-supervised encoder, so you just check the feature similarity between 2 frames.
So if the Dino v2 features are really similar, the camera probably didn't move much, so it's an easy pair. If they're very different, it was a big movement, and it's a hard pair.
Exactly. And they use this to build a training schedule. Over time, the curriculum progress, this parameters is, gradually lowers the bar for required visual overlap. It forces the model to tackle those really challenging wide baseline views, but only after it's built a solid geometric foundation on the easy stuff.
Let's pivot to the results then, because a clever architecture is one thing, but does it actually perform better? How does E-RASER do against RASER and the big, fully supervised models?
Well, first, just comparing to RASER, the self-supervised baseline, the improvement is dramatic. The key metric here is relational pose accuracy, or RPA. It just measures how close the predicted camera angle is to the ground truth.
And what are we seeing in the numbers?
The difference is night and day, especially on the strict metrics. On the DL3DV dataset, for the RPA at 5-degree threshold, RASER scores a 0.0.
A 0.
A 0. It basically never gets that precise, which really confirms it wasn't learning real geometry. E-RASER on that same metric jumps to 72.0. It's just a massive leap, and it's clear proof that the new architecture is learning genuinely 3D-aware representations.
Okay, but the real test is how this self-supervised model does against a model trained with high-quality pseudo-labels. How does it stack up against the supervised state-of-the-art VGGT?
And this is where it gets really exciting for the field. On several out-of-domain datasets, so data it's never seen before, E-RASER performs on par with, or in some cases, better than the fully supervised VGGT. It's often more accurate on that stricter 5-degree metric, which suggests it's learning a more precise and generalizable representation, even without any labels.
That's a huge result. Unsupervised beating supervised on generalization. What about for more practical use? Can you use E-RASER as a pre-training step for a supervised model?
Absolutely. And it works incredibly well. If you initialize a VGGT model with the E-RASER weights instead of starting from scratch, you get significant performance boosts across the board. For instance, on DL3DV, the RPA at 15-degree metric jumps from 94.2 up to 96.6. It clearly shows that the spatial knowledge learned during self-supervision is highly complementary to what's learned during supervised fine-tuning.
Now, for the ML engineers listening, the real treasure is often in the encoder itself. How well do these learned features transfer to other 3D tasks if you just freeze the backbone?
This is where E-RASER really proves its worth. On multi-view depth and pose estimation, it's the clear winner. With a frozen backbone, E-RASER just significantly outperforms all the other major visual encoders they tested. Dino V2, Croco V2, Video MAE V2, all of them.
Can you give us a specific number on that?
Sure. On the ScanNet plus depth estimation task looking at absolute relative error, E-RASER gets 0.116. For comparison, RASER gets 0.161 and Video MAE V2 gets 0.175. It's not a small margin. It's a huge improvement, and it confirms that this explicit 3D modeling really does lead to better, more structured features.
And if you unfreeze it and allow full fine-tuning,
the lead holds. E-RASER gets the best performance across all the datasets and metrics they tested. If you look at the feature visualizations in the paper, it's obvious why. The E-RASER features are so much cleaner and more spatial consistent. They clearly outline the major 3D structures in the scene, which is exactly what you want from a pre-trained encoder.
what about for something like a 2.5D task, say pairwise flow estimation? Is that a place where maybe the implicit model, RASER, would have an edge since it was sort of optimized for that kind of motion?
That's a great question. And yes, RASER does hold a very slight edge there. E-RASER is still highly competitive on the Static Things 3D dataset, but RASER is just a hair better. And the thinking is that its implicit nature, while bad for true 3D, is a little better suited for that kind of dense, low-level motion estimation. But, and this is important, E-RASER still soundly beat other strong baselines like Croco V2. So even for 2.5D, its features are very meaningful.
Let's wrap up with the ablations on data and curriculum, because there's a really critical insight in here for anyone thinking about building these large 3D models. We see that E-RASER scales with data, which is what you'd expect. But there's this fascinating point about data quality versus just raw quantity.
This might be the most important takeaway from the whole paper for future research. They trained one model on a smaller, high-quality data set called DL3DV, which has about 10,000 sequences. And they trained another on a much larger but noisier data set called Spatial Vid with 100,000 sequences.
So 10 times more data.
10 times the data. And the model trained on the smaller, higher-quality data set significantly outperformed the model trained on the massive, noisy one on every single domain they tested.
Wow. That really flies in the face of the standard more data is always better foundation model mindset. It suggests you can't just throw millions of random YouTube videos at this problem and expect it to work.
Exactly. The results are a strong signal that for 3D self-supervision, data quality and diversity are the real drivers of scalability, not just the raw number of sequences. Specifically, data with diverse and challenging camera movements and data that doesn't have a lot of distracting moving objects. That's what provides the best signal for learning geometry. It's a really valuable guide for how we should be curating data.
So we should be looking for data that's harder to solve but geometrically clean, not just data that's easy to find.
That's the takeaway. The challenge shifts from model engineering to data engineering.
And just to close the loop, the curriculum was definitely essential to this whole thing working.
Oh, absolutely. The ablations show that both the semantic and geometric overlap curricula were way better than a simple frame interval approach, and especially better than having no curriculum at all. It just reinforces that you need that careful, adaptive control over difficulty to get these explicit 3D models to train stably from scratch.
So we started this whole discussion with this idea that self-supervised 3D was kind of stuck, relying on these fragile pseudo-labels and clever but ultimately flawed shortcuts.
And E-RASER really breaks out of that. By forcing geometric grounding with explicit 3D Gaussians and stabilizing the whole process with a smart curriculum, it finally unlocks stable, self-supervised 3D reconstruction from scratch. And it's doing it at a level that's competitive with, and sometimes better than, fully supervised methods, particularly when you look at generalization.
So what's the final message for you, the researcher or the engineer who wants to build better 3D perception systems? It seems to be that you can now seriously consider leveraging massive amounts of unlabeled video to build these foundational 3D models without that huge bottleneck of 3D labeling or relying on brittle SFM.
And if you want to connect this to the even bigger picture, I think E-RASER's success points to a fundamental shift in where we should be focusing our efforts. It suggests that the real bottleneck for large, scalable 3D vision models isn't the supervision method anymore, it's the data itself. The future isn't just about better models, it's about better data curation. Finding and selecting for that high-quality, geometrically challenging data. That's the next frontier.